Definition of porphyry copper-gold deposit. A porphyry copper-gold deposit is a large, disseminated mineral deposit that forms in association with intrusive igneous rocks, typically porphyritic in texture, meaning they contain large, well-formed crystals set in a fine-grained groundmass. These deposits are created when metal-bearing magmas intrude into the Earth's crust and release hydrothermal fluids. As these fluids circulate through surrounding rocks, they precipitate copper, gold, and other metals within networks of fractures, stockworks, and veins, as well as finely dispersed within the host rock. Porphyry copper-gold systems are among the most important sources of copper and also contain significant amounts of gold, molybdenum, and sometimes silver. The mineralization usually occurs over a very large area, with ore distributed at relatively low grades but in volumes large enough to be mined profitably through large-scale open-pit methods. Geologically, these deposits form in tectonic settings related to convergent plate boundaries, especially in magmatic arcs above subduction zones. The intrusive bodies involved are often granitoid in composition and emplaced at shallow to intermediate crustal levels. The mineralization is closely linked with alteration zones, which display distinct concentric patterns, a potassic core rich in biotite and magnetite, surrounded by phyllic, sericite quartz, argillic, and propylitic alteration halos. From an economic perspective, porphyry copper-gold deposits are extremely significant because they supply a large proportion of the world's copper and gold. Famous examples include the Grubberg deposit in Indonesia, Bingham Canyon in the United States, and Oyu Tolgoi in Mongolia. Their size, longevity, and metal endowment make them cornerstone resources for global mining industries. Formation of porphyry copper-gold deposit. Formation of porphyry copper-gold deposits. The formation of a porphyry copper-gold deposit is a complex, multi-stage geological process that begins deep within the Earth's crust and upper mantle and continues through a series of magmatic and hydrothermal events. These deposits are closely tied to plate tectonic activity, particularly in subduction zone environments where oceanic crust is forced beneath continental or island arc lithosphere. 1. Magma generation in subduction zones. As the oceanic plate descends into the mantle, it releases water and other volatiles into the overlying mantle wedge. This addition of volatiles lowers the melting point of the mantle material, generating hydrous, metal-rich magmas. These magmas are typically calc-alkaline in composition and enriched in copper, gold, and other trace metals. 2. Magma ascent and intrusion. The buoyant magmas rise through the crust and often stall at shallow to mid-crustal levels, 2 to 10 kilometers depth. During this stage, the magma begins to crystallize slowly, producing a porphyritic texture, large crystals of feldspar, quartz, or biotite within a finer matrix. Repeated pulses of magma may intrude the same area, building large intrusive complexes known as porphyry stocks. 3. Exsolution of hydrothermal fluids. As the magma continues to cool, pressure decreases, and water along with dissolved metals and sulfur exhale from the magma in the form of hydrothermal fluids. These fluids are initially supercritical, a mixture of vapor and brine, capable of carrying large amounts of metals. The release of these fluids is one of the most critical steps in forming ore. 4. Hydrothermal fluid circulation and metal deposition. The hydrothermal fluids migrate upward and outward from the cooling intrusion, moving through fractures, faults, and permeable zones in the surrounding rocks. As they circulate, they precipitate copper, as chalcopyrite and bornite, and gold, often along with molybdenum, silver, and other metals. Deposition occurs when the fluids cool, mix with groundwater, or react chemically with the host rocks, causing metals to drop out of solution. 5. Development of alteration zones. The interaction of hot hydrothermal fluids with country rocks creates distinct alteration halos around the intrusion. Potassic alteration, core characterized by secondary biotite, K-feldspar, magnetite, and associated with high copper and gold grades. Phyllic alteration, dominated by sericite and quartz, surrounding the potassic zone, often carrying lower-grade mineralization. Argillic alteration includes clay minerals, kaolinite, smectite, usually formed at shallow levels. Propylitic alteration, the outermost halo, with chlorite, epidote, and carbonate, generally weak in or minerals. These alteration zones are diagnostic indicators for geologists exploring porphyry systems. 6. Supergene enrichment, secondary stage. After initial mineralization, near-surface weathering and oxidation can enhance ore grades. Rainwater and oxygen leach copper from the upper portions of the deposit and redeposit it at depth as secondary sulfides, chalcocite, covellite. This process, known as supergene enrichment, significantly increases the economic value of porphyry deposits. 7. Final characteristics. The result is a large, low, to medium-grade deposit with copper and gold mineralization distributed over several kilometers. The ore is typically disseminated, spread out as fine grains in host rocks, but also occurs in stockwork vein networks and breccias. Economically, these deposits are enormous in scale, containing billions of tons of ore, which allows them to be mined by large-scale open-pit methods. Summary. Porphyry copper-gold deposits form through the combination of subduction-related magmatism, porphyritic intrusions, exsolution of hydrothermal fluids, metal transport, and precipitation within fracture networks, followed by alteration and sometimes supergene enrichment. Their unique geological setting and formation process explain why they are the world's leading source of copper and a significant source of gold. Properties of porphyry copper-gold deposits. Porphyry copper-gold deposits are among the world's most significant sources of copper and an important source of gold. They are defined by a unique set of geological, mineralogical, geochemical, structural, and economic properties that make them distinct from other deposit types. 1. Geological properties. Host rocks. These deposits are typically associated with porphyritic intrusions of intermediate to felsic composition, granodiorite, quartz monzonite, tonalite. The porphyritic texture reflects two stages of magma crystallization. Tectonic setting. Most form in magmatic arcs above subduction zones, where oceanic lithosphere descends beneath continental or island arc crust. Some also form in post-collisional or extensional settings. Size and shape. They are very large systems, often several kilometers across and extending to great depths. The ore body is usually centered on an intrusive stock, with mineralization spreading outward in a roughly cylindrical or elliptical pattern. 2. Mineralogical properties. Ore minerals. Copper, primarily chalcopyrite, bornite, chalcocite, and covellite. Gold, present as microscopic inclusions in sulfide minerals, chalcopyrite, pyrite, bornite, or as native gold. Other metals, molybdenite, molybdenum, enargite, arsenic, sphalerite, zinc, galena, lead, and traces of silver. Gangue minerals. Quartz, feldspars, biotite, magnetite, cerussite, chlorite, carbonates, and clay minerals. 3. Alteration properties. Hydrothermal alteration is a key diagnostic feature of porphyry deposits. Distinct concentric zones of alteration surround the mineralized intrusion. Potassic alteration, core zone biotite, K-feldspar, magnetite, hosts the richest copper-gold mineralization. Phyllic alteration, intermediate zone quartz plus cerussite plus pyrite, commonly associated with moderate mineralization. Argillic alteration, shallow zone clay minerals, kaolinite, smectite, may host supergene enrichment. Propylitic alteration, outer zone chlorite, epidote, carbonate, usually weakly mineralized. These alteration zones provide exploration geologists with reliable guides to ore. 4. Structural properties. Fractures and veins. Mineralization is controlled by networks of fractures and stockwork veins, where hydrothermal fluids deposited or minerals. Breccia zones. Some deposits include hydrothermal breccias filled with sulfides and gangue. Scale of veining. Stockwork veinlets can number thousands per cubic meter, providing the disseminated nature of mineralization. 5. Geochemical properties. Metal ratios. Characteristically copper-dominant, with variable gold content. Some are copper-molybdenum-gold or copper-gold-silver. Sulfur content. High sulfur content, essential for transporting metals in solution as sulfide complexes. Oxidation states. Copper is commonly found as sulfides, but secondary enrichment may produce supergene oxides and enriched sulfides near the surface. 6. Physical properties. Grade and tonnage. Typical copper grades, 0.3 to 1% Cu. Gold grades, 0.1 to 1.5 grams per ton O, though even low-grade gold can be valuable due to large tonnage. Or tonnage, hundreds of millions to billions of tons. Deposit scale. Large enough to support decades of mining, some have been mined continuously for over a century, e.g., Bingham Canyon, Utah. 7. Economic properties. Mining method. Because of their large size and low to medium grades, they are typically mined by large-scale open-pit operations, though deeper parts may be mined underground, block caving. Byproducts. Besides copper and gold, many porphyry deposits yield molybdenum, silver, rhenium, and other byproducts, increasing their economic value. Global importance. They account for about 60 to 70% of the world's copper and a major share of global gold production. 8. Exploration properties. Geophysical signatures. Magnetic highs, due to magnetite in potassic core. IP, induced polarization, anomalies from disseminated sulfides. Geochemical signatures. Elevated Cu, O, Mo, and pathfinder elements such as Sb, and Te in soils and rocks. Surface expression. Alteration halos, gaussons, leached caps, and supergene enrichment zones are often detectable at surface. Summary. Porphyry copper-gold deposits are large, low, to medium grade, disseminated or bodies characterized by their association with porphyritic intrusions, hydrothermal alteration halos, and extensive fracture-controlled mineralization. Their combination of size, metal content, and longevity makes them the backbone of the world's copper and an important source of gold.